Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asghar, and today the topic of our discussion is fundamentals of dynamic mechanical analysis (DMA) under the subject of thermal analysis. So first of all, we should have to be aware with some of the renowned terminologies that is used in lectures, in our different lectures. First is rheology. The term rheology was coined by Professor Bingham of Latrobe College. He was professor in Indiana University at USA. Professor described it as the science of flow and deformation of materials, a definition accepted by American Society of Rheology in 1929. Howard said that the flow was a deformation, at least part of which was non-recoverable. Later on, William considered deformation a change in shape. For the point of view of Russell, rheology was actually the study of stress deformation relationships, allowing one to analyze the consecutive equations linking the stress and deformations in materials. While according to N.W. Tesogel, a consecutive equation or rheological equation of the state finds actually a relationship between a dynamic quantity, stress, and kinematic quantity, strain, through which one or more parameters are functions representing the characteristic response of the material per unit volume. It is actually regardless of the size and shape. DMA is actually dynamic mechanical analysis studies the behavior of materials which are subjected to a dynamic or steady deformation. It looks at how they respond to an imposed stress. Stress deforms the material and DMA measures the strain, calculating how much energy is stored and dissipated during the whole process. Although gels and some viscous samples can be tested, a DMA instrument is specially adapted to the rheological study of solid state like materials. Dynamic mechanical analysis, which is actually DMA, is also considered to be a good thermal analysis technique because the temperature can be controlled during the whole test. Thermal properties such as glass transition TG, which we have studied a lot in our previous lectures, and it can be studied by means of DMA. Flow and deformation parameters. Let us consider some of the parameters of flow and deformations. Since any rheological study deals with deformation and stress, the following terms will be used consistently. Stress is actually the force deforming the sample per unit area. The SI units of stress are usually pascals. Tau or rho is equal to F over A, while strain is actually a distance the distance a sample moves in response to the relative to sample length. It has no units. So this is actually the ratio, and it do not possess any kind of units. So what is the major difference between stress and strain? Stress is actually the force deforming the sample per unit area, and we already studied the SI unit is Pascal for stress, while strain is the distance a sample moves in response relative to the sample length, and we know that strain have no units. Strain rate is actually the change of shear strain per unit time. It is represented by omega in shear and epsilon in tensile. Its units are per second. So, what are the ideal and real behaviors? The range of a material's rheological behavior falls between the two classical extremes. The two classical extremes are ideal solution solid and ideal fluid. They are described by Hooke and Newton's law. So we need to study Hooke and then Newton law respectively. Hooke's law. Hooke describes the behavior of an ideal elastic solid relating to the applied strain to the resultant stress, or vice versa. The proportionality factor is called the material's modulus and is denoted as E or sometimes G capital. Young's modulus. It is the ratio of dynamic stress to strain. E star is actually measured in tensile or bending mode. E is equal to sigma over epsilon, while the shear modulus is the ratio of dynamic stress to the strain. Newton's law is actually describe the behavior of ideal fluids according to the stress and shear. The proportionality factor is viscosity. Ideal viscous fluids are linear in terms of shear rate, not shear thinning. In order to distinguish between Newtonian and non-Newtonian behaviors, it is imperative to bear in mind that the shear viscosity of Newtonian fluids does not vary with shear rate and is constant with time of shearing. Now let's talk about the actual materials. The actual materials are linear or non-linear regions. Most materials obey these laws over a limited range of stress. Beyond this range, they show non-linear behavior. This unit will provide examples of how material actually behaves. So we know that there are two laws that we have studied so far: Hooke's law and Newton's law. Hooke's law was actually the description of the behavior of an ideal elastic solid, relating the applied strain to the resultant stress, or we can change it vice versa. While in case of Newton law, it actually describes the behavior of ideal fluids according to the stress and shear. This figure 1 actually shows the strain stress plot obtained from a wire made from a nickel titanium alloy, which is written over there, and subjected to the DMA, dynamic mechanical analysis. The behavior is similar to that of an ideal solid unit breaking point. One finds in figure 2 the typical strain stress plot obtained from a thermoplastic polymer. In this case, after the linear region, there is a wide range of non-linear behavior where creep is involved. Most polymer melts reveal a viscosity dependence with a shear rate as shown in this figure 3, with the linear region for a low shear rate and shear thinning for higher shear rates. Now the non-Newtonian time independent liquids. Liquid viscosity is dependent on the shear rate but independent of the time of shearing. The following cases are possible: pseudoplasticity. It is actually the viscosity decreases while the shear rate increases. This is also known as shear thinning. The second is dilatancy or shear thickening, in which both viscosity and shear rate increase. While the third one is Bingham fluids, in which there is no deformation below a yield stress. Above yield stress, the behavior may be Newtonian or non-Newtonian. Figure this figure 4 actually summarizes the Newtonian and non-Newtonian time independent flow types. Non-Newtonian time dependent liquids. The viscosity of a fluid is dependent on the shear rate and the time during which shear rate is applied. There are two typical cases. Number one is thixotrophy. It is apparent to the viscosity decreases time under constant shear rate or shear stress. This is followed by a gradual recovery when the stress or shear rate is removed. The second after thixotrophy is rheopexy. Rheopexy is an increase in apparent viscosity appears with time under constant shear rate or shear stress. There is a gradual recovery when the stress or shear rate is removed. Here is the idealized plot which is showing the viscosity and a time dependence on shear rate and time in a thixotrophic fluid. Now, viscoelasticity. We have to study the phenomena where viscoelasticity is involved. Viscoelasticity is actually the word which is used to describe the material behaviors found among ideal solids and liquids. Examples in which viscosity effects are very evident include the rate dependent behavior in solids. Solids in general behavior with greater stiffness at high deformation rates. Silly putty is a silicon in which a dramatic change of stiffness occurs at deformation rates that fall under normal use. The second one is rod clamping in liquids. Newtonian and viscoelastic behaviors of a liquid subjected to stirring action. Viscoelastic liquids tend to climb the stirring rod. The third one is dye swell in the extrusion of thermoplastics, which is actually showing in this diagram. This is the dye swell in extrusion. This is extruder die and we can see dye swell in extrusion. The next one is the plastic memory. In the injection molding of thermoplastics, it is well known that if the mold is open and when the temperature of a pot is still high, the pot tends to twist, remembering the movement imposed by the screw in the extruder. The next one is the melt fracture. one of the most frequent problems in extrusion. It is also related to the deformation rate when a material passes through a nozzle. And this melt fracture is represented in figure 8. We can see this is the melt fracture. It is one of the most frequent problems in extrusion. It is related to the deformation rate when a material passes through the nozzle. So these are the diagrams of die swell in extrusion and melt fracture. The next one is viscoelasticity and time dependence. Nothing behaves like an ideal solid or an ideal liquid. This fact seems to be reinforced by saying like everything flows if you wait long enough. So nothing behaves like an ideal solid or an ideal liquid. Actually, apart from the case of the last one studied silicon, which was the silly putty mentioned above, there are also many examples in nature and in real life. Ice is considered a solid, but it is well known that glaciers have flowed over millennia. Another case in point is how old stained glass windows in European buildings is reported to be thicker at the bottom. This phenomenon is actually attributed to the slow flow of the glass while in place. We have already studied and may observe in old buildings that the glass windows are the glass materials of that particular buildings is actually have a thicker mass at the bottom while it somehow thinner at the upper side of the window. And this phenomena is attributed to the actually slow flow of glass, which is sometimes also known as creep. This is creep is the slow flow of glass. We know that water is a liquid, although have an impact at high speed against water may cause damage. This high speed damage may be because with high speed deformation water behaves more like a solid. So the time scale is critical. The time scale is critical with the solid like behavior being favored by short time scales, the liquid like behavior by longer time scales. This is all that we have studied so far in the fundamentals of DMA, and we also studied flow and deformation parameters along with ideal and real behaviors, Hooke's and Newton's law, and some linear and non-linear regions. Lastly, we studied non-Newtonian time-independent liquids and viscoelasticity and time dependence. This is so far this lecture. Thank you very much.